On January 10th of 2022, a critical vulnerability was disclosed to Multichain, formerly known as Anyswap, by the Debaub team. Multichain made a public announcement a week later stating a critical vulnerability that affected 6 cross-chain tokens was reported and told users to remove any approvals of these 6 tokens for their system. On Ethereum alone, $431 million of WETH could have been stolen in a single direct transaction from just 3 victim accounts. In this video, I'll be going over the vulnerability itself and how to write a proof of concept that would have allowed us to steal hundreds of millions of dollars. Welcome to the Dark Forest. Before getting into Multichain's code, let's review the ERC20 token standard WETH implements. The ERC20 token standard defines functionalities that tokens should have, such as getting an account's balance, transferring those tokens, and getting the total supply. This helps developers build applications which use these tokens by standardizing the methods they can expect. ERC20 tokens are also fungible, meaning each token is equivalent to each other. This is similar to how most currencies work. My $1 bill is exactly equivalent in value to your $1 bill. To be considered an ERC20 token, the following methods must be implemented. Total supply, which returns the total amount of minted tokens. Balance of, which returns the balance of the past account. Transfer, which transfers some value of tokens from the caller of the function to the past to address. Transfer from, which transfers some value of tokens from the past from address to the past to address. Approve, which allows a spender to transfer your tokens up to the value specified. And allowance, which returns the amount of the owner's tokens a spender is allowed to transfer. WETH wraps Ethereum's native currency ETH and implements the ERC20 token standard on top of it to allow for easier integration to decentralized applications. A user deposits ETH into the WETH contract and gets an equivalent number of WETH tokens. Each token is 100% backed by ETH locked in the WETH contract. Now that we have an overview of the ERC20 token standard and how WETH implements this, let's take a look at Multichain's contract. Multichain had a vulnerability in their Anyswap v5 ERC20 contract, specifically within the deposit with permit function. To understand the purpose of deposit with permit, let's first take a look at deposit. Deposit transfers tokens from the message sender to this contract. Save transfer from just wraps the transfer from function to perform some additional checks, but we can ignore this and treat this like a normal transfer from. The use of transfer from relies on an approval of the Anyswap contract before making the call to deposit. The use of message sender means the contract can only transfer your tokens if you have made an approval and are the initiator of the call to deposit. This means the user must make 2 transactions, the approval and the deposit. However, there is a second path to deposit funds. Deposit with permit allows depositing of funds by a relayer. This means the user depositing funds does not need to be the account to call deposit with permit, and the approval and transfer can occur in one transaction. Permit was introduced in EIP2612 and is a meta-transaction pattern. Permit extends the ERC20 token standard and allows users to modify the allowance mapping using the account derived from an off-chain signed message instead of through message sender. This improves user experience by allowing the approval and transfer from to occur in a single transaction rather than 2 separate ones. As defined in the EIP, the call to permit will set an approval as long as the following conditions are met. The current block time is less than or equal to deadline. Owner is not the 0 address. The nonce is correct. And the RS and V values is a valid signature from the owner of the message. If any conditions are not met, the permit call must revert. Now let's take a look back at the deposit with permit function. Permit is being relied on to perform an important security check, verifying the signature is valid. This is where the billion-dollar mistake was made. Not every ERC20 compatible token implements permit. WETH does not define a permit function. It does, however, define a payable fallback function. When deposit with permit calls permit on WETH, the fallback function is invoked, since no other functions match the permit function signature. This fallback function calls WETH's deposit. Message value is 0, so there is no change to the balance, and the call emits an event and returns successfully. None of the parameters passed to the permit call are checked. It's basically like the call to permit was never even there. Now you might think, that's fine. The contract won't be able to use safe transfer from to transfer the target's tokens since the call to permit did nothing and no new allowance was set. But if a target had made an approval to the Anyswap v5 ERC20 contract in the past, the contract will already have an allowance set and the safe transfer from will succeed. The tokens deposited can then be attributed to the attacker by specifying their address in the to parameter. All with an account approved the Anyswap v5 ERC20 contract to transfer can be stolen by a call to deposit with permit passing the victim's address, the amount the victim approved the Anyswap contract to use, any arbitrary values for the deadline and signatures since they are not being validated, and finally, the attacker's address. Using this new knowledge, let's take a look at how we can create a proof of concept to demonstrate the impact of the vulnerability in deposit with permit. I'll be using hardhat and writing waffle tests in JavaScript since I'm most familiar with this setup. Node.js is required to run hardhat. So first, take a look at the hardhat documentation to find out how to install Node for your operating system. We'll also be forking the Ethereum mainnet for our test, so sign up for a free Infura or Alchemy account and set up an Ethereum mainnet project. I set up an account with Alchemy and selected Create App. I called mine mainnet forking, selected development for my environment, Ethereum for the chain, and mainnet for the network. Keep this API key handy for later on. After you've set up your mainnet node and installed Node.js, let's go ahead and create a folder for our PoC. I'll call this Anyswap PoC and then cd into the directory. Run npm init with the yes flag to auto-accept any prompts. This will create a package.json file that will keep track of our project's dependencies. Next, to install hardhat, run npm install --save--dev hardhat. This saves hardhat as a developer dependency in our package.json. Hardhat lets us compile, deploy, test, and debug Ethereum smart contracts and will provide us with the tools needed to test our vulnerability. Once hardhat is installed, we can create a new project by typing npx hardhat. Let's select Create a Basic Sample Project so we don't have to create all the necessary folders from scratch. Press Enter to set the project root to the current directory, then choose Yes for adding a git ignore, and Yes to installing the Waffle and Ether.js dependencies that we'll need for writing our test. Once the setup completes, you'll see a contracts folder, which contains the source code for our Ethereum contracts, a node modules, which we can ignore but includes code for all of our dependencies, such as Ether.js and Waffle, a scripts folder, which contains automation scripts, and a test folder, which contains all tests that will be run when initiated through hardhat. In addition to these new folders, you'll see a few new files. Package.lock.json and the README can be ignored. The file we want to focus our attention on now is hardhat.config.js. The entirety of your hardhat setup is contained in this file. Module.exports is used to define all the configuration variables we'll need to set up our hardhat project. This includes the Solidity compiler version, what network you want to deploy to, what directories our sources and artifacts are in, and a whole slew of options that you can read over in the hardhat documentation. For our PoC, however, all we need to define is the network we're using. Create a new property, networks, at the root level of the module export, and within this define a network called hardhat. Inside of that, we're going to tell hardhat we want to create a fork of a network, and pass in the URL to our node we created with Alchemy earlier. I'm going to pass the URL in with an environment variable to make changing this value easier, and to prevent myself from checking in sensitive information to my GitHub repository. When forking, hardhat also allows you to define a block number you would like to pin the fork to. Hardhat network, by default, will fork from the latest mainnet block. Since the vulnerability has already been disclosed and mitigated, that won't work for us. What pinning allows us to do is to revert the state back to a specified block and continue creating new blocks from that point instead. In Debaub's article, they mentioned the Phantom Bridge was vulnerable and had a large amount of WETH. Using BigQuery, I crafted a query that returned any transactions in which the Phantom Bridge made an approval for WETH. With the results of the query, I found in block 13,906,273, the Phantom Bridge made an approval to the Anyswap v5 ERC20 contract. We can define a block number in our forking object and start our network from the block the approval occurred in. Now that we have a forked mainnet set up, let's move on to writing the test. We want to interact with the Anyswap v5 ERC20 contract to exploit the deposit with permit function. To interact with this contract, we're going to need an ABI. ABI stands for Application Binary Interface and defines basic information about the functions and function types that are available in a smart contract. We could go to the Etherscan page for the Anyswap v5 ERC20 contract and copy and paste the contract code into a local file, then compile the contract this way, but that can get messy with multiple contracts and duplicate contract definitions. An easier way to achieve this is to define our own contract interface that only defines the functions we need to call and use that to generate our ABI. Let's create a new Solidity contract and call it Anyswap v5 ERC20.sol, the I standing for interface. In this file, we'll define the Solidity version we want to compile with, any recent version works, and then create an interface which defines the functions we'd like to use. The only two functions we'll need to execute this exploit is deposit with permit and withdraw. Deposit with permit, as we've gone over, takes the address of the target, the uint256 amount to transfer, the uint256 deadline, a uint8 v value, a bytes32 R and S value, and an address too. The function also returns a uint value. Withdraw takes no parameters and returns a uint value as well. That's all we need for our Anyswap ABI. We'll also need the ABI for ERC20 tokens so we can easily check WETH balances of our bridge and attacker. We don't need to write this from scratch. What we can do is search on the web for ERC20 OpenZeppelin and find the ERC20 interface contract in their GitHub repository. We can copy and paste this contract code into ERC20.sol and save it. Now that we have our contract ABIs, we can start on the actual test. I'm going to remove the greeter contract since we won't be needing this, and open up the sample test. We can remove the code in the test that was automatically generated and update the names of the test. Let's name this set of tests the same as the contract we're testing, and change the test description itself to better describe what we'll be doing. The first thing we want to do in the test function is initialize the addresses of the mainnet contracts we will be interacting with. We're going to be interacting with WETH, the Anyswap v5 ERC20 contract, and we're also going to be needing the Phantom Bridge address. I found these addresses by Googling them and finding their respective Etherscan pages. The const keyword just tells JavaScript that we won't be changing this variable. We can also define the attacker account we'll be using by extracting the first element returned from the ethers.getSigners function. Await tells our code to wait here for the response from this promise before continuing. You can learn more about promises in JavaScript reference guides. To attach a contract ABI to its address, we can use ethers.getContractAt and pass the name of the contract object along with the mainnet address it's located at. For example, for WETH, we could write const WETH equals await ethers.getContractAt ERC20 and the WETH address. Let's do the same for Anyswap v5 ERC20 contract. Const Anyswap v5 ERC20 equals await ethers.getContract at I Anyswap v5 ERC20 and the Anyswap address. We won't be calling any functions on the Phantom bridge, so we don't need to set up anything for that. Now that we have our ABIs attached to their respective address, let's verify the Phantom bridge approval of the Anyswap contract to use its WETH. To do this, we can write let allowance equals await WETH.allowance and pass the Phantom bridge address as the owner and the Anyswap v5 ERC20 contract address as the spender. We can call this allowance function directly on the WETH object since we define this function in our interface contract. Let's go ahead and console log this value and run our test with npx hardhat test. We can see this value is very large. This is actually the max uint256 value, so we know the Phantom bridge has set an infinite allowance for the Anyswap contract to use. Obviously, the bridge doesn't own enough WETH for us to use the entirety of this approval, so let's check how much WETH is actually at risk here. Similar to the allowance call, we can write let bridge balance before equal await WETH.balance of and pass the Phantom bridge address. If we go ahead and console log this out, we can see it's much smaller than the approval, but still substantial. However, this value is in way. To convert to ETH, we can use ethers.utils.formatEther. Now when printed, we can clearly see the number of WETH at risk from just the Phantom bridge alone. 86,866 WETH is at risk from being stolen. Even in today's current prices, that's over 250 million US dollars. Now that we know how much funds are at risk, let's continue on with the proof of concept of our attack. The flaw lied in deposit with permit not checking signatures, so let's call that function. First, we connect our attacker's account before the call to simulate the transaction coming from the attacker's address. Then we call deposit with permit, passing the Phantom bridge's address, the Phantom bridge's total balance before the attack, 0 for the deadline, the 0 byte for V, 32 bytes of 0 for R and S, and finally our attacker's address. This is all it takes to transfer the Phantom bridge's 86,000 WETH out to the Anyswap contract. I'm going to set up a few more print statements so we can get a better idea of what's happening here. If we go ahead and run this test again, we can see the Phantom bridge's WETH balance is 0 after the call to deposit with permit. I'm going to add some more console logs to print the attacker's balance before and after the exploit as well. Running the test another time, we can see that the attacker's balance is still 0 since we haven't withdrawn the stolen WETH from the Anyswap contract. Let's finalize the attack by calling withdraw from the attacker's account. We'll write await Anyswap v5 ERC20 .connect attacker .withdraw. If we run our test now, we'll see the Phantom bridge's balance before the attack was over 86,000 WETH, but after the attacker's call to deposit with permit and withdraw, all WETH has been stolen by our attacker from the Phantom bridge, which had set an approval for the Anyswap contract to transfer all of its WETH. There were close to 5,000 different accounts which had given an infinite approval for WETH to the vulnerable contracts, meaning any WETH those accounts ever acquired were at risk until the approvals were revoked. Luckily, only 0.5% of the funds at risk were stolen by blackhats. Debaub's research and quick disclosure resulted in Multichain narrowly escaping the top of the Rector leaderboard and saved countless user funds. This vulnerability stemmed from WETH token having a default payable function, which was common practice in older versions of Solidity as a hook to receive Ether. However, it also means any call to a function WETH does not implement is essentially a non-failing no-op. Debaub has dubbed this phantom functions. Nowadays, the receive function exists, which is only called when Ether is sent with no call data. This would have prevented the vulnerability, but really, this is a good lesson to projects to ensure backwards compatibility with non-standard tokens, and to thoroughly audit any tokens they do integrate. Many projects have been wrecked by non-standard tokens, such as rebasing tokens, tokens with transfer fees, and tokens which make an external call to receivers on transfers, which can introduce reentrancy. The list of pitfalls always seems to be growing, and that's why projects should heavily invest in their security and incentivize proper disclosure through bug bounty programs like Immunefi. Immunefi provides a platform to bring projects and hackers together so that hackers can report bugs responsibly and projects can fix those vulnerabilities securely. If you'd like to learn more about bug bounty programs which keep DeFi protocols safe, you can visit the Immunefi site and sign up for an account. Who knows, you may be the next white hat to get $1 million bounty payout. And if you've made it this far, thanks for watching.